morning, everyone. We are in the week 7 problem solving session of the NPTEL course Network Analysis, and week 7 is about network theorems. Let me share my screen. Are you able to see my screen? Hello.
Yes, sir.
Okay. So in the earlier weeks, we have discussed about how to solve circuits and how to get the solution of differential equation, and then how to convert into S domain, also how to solve the circuits in polar form, and then we finally moved into S domain. So we have discussed about Laplace transform thoroughly in the last week. So in this week, it's all about network theorem. So for any given network, we know how to solve using different analysis. So whatever analysis that we have learned in the earlier weeks, they are of mainly two analysis. One is the mesh analysis, the other one is the nodal analysis. So these are applicable, and you can apply for any given circuit and you can proceed further. But there are some theorems, just like results, which you can apply to any given circuit wherever they are applicable. And then you can solve the problem in a much simpler way because it saves time. So whenever we get a chance, or wherever we can apply these theorems, if we could apply those theorems, then the problem can be solved in a much simpler way, and it also saves our time. So in this week, we'll mainly discuss about network theorems. So first I'll be discussing about some brief explanation of this network theorems before we go into problem solving session. But if I get time, I will show the proof. But if I start with proving those theorems, then I don't think we'll get time to solve few problems. So first I'll just give a brief explanation of what that theorem means and how to apply some brief discussion. So first we'll start with the superposition theorem. Next we'll go to substitution theorem. Okay. Next, we'll be going to Thevenin's theorem. So I hope you have all of you gone through whatever Sir has taught in this lectures, because then you will be able to easily understand what this theorem means. And then Norton's theorem. I'm audible, right? Yeah, someone has mentioned in the chat. Yes, sir. Okay. And then fifth, we have compensation theorem. And sixth, we have Tellegen's theorem. And finally, we have reciprocity theorem. Okay, we'll just go one by one. We'll start with superposition theorem, and I'll probably give some definition so that you can read the definition and you can understand what it means. Okay, first we'll start with the substitution theorem. So can anyone tell me what is substitute theorem? Superposition theorem is all about? Anyone?
Solving the network using one source at a time.
Yes. So if any given circuit has multiple voltage or current sources, Then if we want to find a voltage or current in one element, then the voltage or current in that element is just algebraic sum of the currents in that element when we consider one source at a time. So if we want to write that, so in a all of these are applicable for linear circuits only. So keep that in a linear circuit. With multiple voltage and current sources. The response of any element. So when I say response, it could be current or it could be voltage. So the response of an element, it could be RLC, is the algebraic sum of the responses of that element obtained by considering one source at a time. So say by considering one source at a time. So I have one voltage source, one current source. So when I consider voltage source, what I need to do with the current source, and when I consider current source, what should I do with the voltage source? Anyone? Which is also quite important.
Sir, we will replace by its internal impedance.
Yes, yes, you're right. So if there is no internal impedance, then
Sir, if
Voltage source
voltage
must be short circuited and current source will be open circuit.
yes, yes, you are right. So let us just quickly take one circuit. I will not be going to solve this. That will solve like when we go to the previous year assignments the solving session. But I'll just take one circuit and I'll just show how to proceed. I think blue color is not looking good. We'll show some other color. So I have considered something like this, and I'll not take any values. This is in general. So I'll consider V1, V2, I. This is R1. This is R2. This is R3. This is R4. So my question is find this resistance small I. So how will I find? Anyone?
Sir, all the sources are ideal or
Ideal. So for voltage source, the impedance is zero, series impedance, and for current source, the parallel resistance is infinite.
sir, we can replace the voltage and current source as short circuit and open circuit respectively and find out the current.
Yes.
Due to
Yeah. So we'll consider. Sorry. Continue.
so similarly, other sources can be considered and algebraic sum of current can be used to obtain the
Yes, yes. So we'll consider one source at a time, and accordingly, we'll either short the voltage source or open the current source. So if we just get the three circuits, so first I'm considering V1, so I'll short V2, and then I'll open I. So this is still R1, this is R3, R2, R4, V1. So the current because of V1, I'm considering I1. So plus. So this is one source. Now I'll have to consider another source. Now I'll consider V2. Okay. And I will still not consider I. R1, R3, R2, V2. And this is R4 and current say I2. Now I'll consider I. So R1, R2, R3, R4, and current I. So we have shorted the other sources as we are considering only the current source. The other source to be shortened. And this is R4 and this is our current I. And here we have I3. So applying superposition algebraic sum. Just one thing you need to keep in mind, the current that I have asked is in the downward direction. So by default, I have considered I1, I2, I3 in downward direction. So I can add. Whereas if you are getting the current in the opposite direction, then you have to consider that sign also. And so that's why it is always good if you can consider the current in the same direction, then you can directly add. So I'll not care about the direction of the current. So I'll always consider the current to be downwards. So if it is actually flowing downwards, I'll consider positive, else I'll consider negative. So now my I is I1 plus I2 plus I3. So this is the final thing. So similarly, if there are n number of sources, we'll consider one at a time, and accordingly, we'll either short the voltage source or open the current source, and we'll proceed accordingly. So is this clear until this point? The superposition theorem. If you have any doubts, you may ask. Else we can proceed with the substitution theorem. Okay, I hope you don't have any queries, but you may stop at any time. Substitution theorem. So anyone? Yes, sir, clear. Okay. So substitution theorem is like in any given linear circuit, say there are a number of elements, and we have considered one element, say resistor R. It can be either converted to a voltage source, equivalent voltage source, or equivalent current source. So yeah, linear circuit with again multiple sources can be there. That is assumed with multiple sources. I am not mentioning voltage or current because there could be any source with multiple in a linear circuit with multiple sources. A resistor element, say we are talking about a resistor element, a resistor element can be replaced by an equivalent voltage source or current source. So either if you want to convert it to voltage source, that is fine, or current source. It's not both. So either you can convert it into a voltage source or current source. Voltage source or current source. So first we'll start with a simple circuit to understand how it is working. Then we'll move on to say when I say equivalent voltage or equivalent current source. First I'll start with some two resistors so that we can better understand the concept. I have considered R1, R2, right? So R1, R2, and say the input is Vin. Okay, now can someone tell me what is the current? Or can you tell me what is the voltage across this resistor? Say V1. Anyone?
V minus I R1.
Okay, but say if I want only in R1, R2, and V. Say in terms of R2, R1, or V.
I is equals to V divided by R1 plus R2.
Okay.
By substitution.
Yes. Yeah, so or else I can directly say R2 by R1 plus R2 into V. Right. So R2 by R1 plus R2 into V. And my I is nothing but V in by R1 plus R2. Oh. So these are my voltage and current. So now what I'm trying to say is in this linear circuit, say any resistive element, this resistive element R2 can be replaced by an equivalent voltage source. Equivalent voltage source means what is the voltage across this resistor? Here V1 is R2 by R1 plus R2 into V. So I can replace this R2 by this voltage source and the circuit remains unchanged. So I will show you how it will still remain unchanged. So now the modified circuit, which will replace it by a voltage source. So I can replace it by voltage source without violating KVL or KCL. So that is the whole point. So this is my V in, this is my V1, and this is my R1, and this is my current I. So now in this case, what will be my current I? My current I is V in minus V1 by R1. Do you agree? In this case,
Yes,
the new circuit. So I will bring the R1 outside, and V in is V in, and V1, what is the V1? This is the same value, right? Because when I say equivalent, so the equivalent term is very important. So whatever is the voltage that is flowing, so the across that resistor, we need to replace that resistor by with that voltage source only. So V1 is R2 by R1 plus R2 into V. So if you simplify this, I will get I is equals to 1 by R1 into V into R1 by R1 plus R2. That implies my I is V in by R1 plus R2. So my current is not changed. So even if I have replaced it by an equivalent voltage source, my current has not changed. So whatever current that the source is supplying in my earlier circuit, it is still supplying in this circuit. However, I have converted this resistor into voltage source. So just for my ease, I have converted, and I'm trying to prove that it still remains same. The circuit is still remain the same, and the KVL or KCL, nothing is violated. So this is when I have converted that this what do I call this resistive element into a voltage source. Similarly, I can connect or convert this resistor into a current source. I can also do that. So let me do that. So you are understanding, right? Whatever I'm trying to prove.
yes, sir.
Yes. So now I'll consider a current source. And what will be the direction of the current source? That is very crucial. Upwards or downwards? How the current is flowing from top to bottom or bottom to top? In the R2. It is flowing like this, right?
Top to bottom.
Yes, yes. So top to bottom. So I have to consider the current source in the exact way with the magnitude whatever we have obtained here. V in by R1 plus R2. So the magnitude is V in by R1 plus R2. So now this much of current is flowing. So if this current is flowing, the same current will flow in this uh, R1 element as well. Now, in the first case, so if I consider this as case one, say I am considering this as case one. Case one is when I have considered the equivalent voltage source. Case two, I am considering equivalent current source. So when I convert this into equivalent voltage source, current is unknown, and I have found the current which is exactly matching with my earlier values. Now, in the case of current source, voltage is unknown, so I will find the voltage across this element or this source, current source now, and I'll see whether it is matching with my earlier expression or not. So the idea is to, or the objective is to find this voltage. Say this voltage is some V dash. So can anyone tell me what is the expression of V dash? Because I know the current through R1 and I know the potential here. So this minus the potential difference across R will give me this potential. So this is V and this is what I want to find. So what is the expression? Anyone?
R2 divided by R1 plus R2 into V.
I2, sorry, like I know this current. So I know this current I, which is V in by R1 plus R2. Now I want to find this V dash. So can you tell in terms of V in I and R1?
V minus I into R1.
Yes, V in minus I into R1. So R1 into I. I is already known because we have converted that into a current source by R1 plus R2. If you simplify, you will be getting V dash is equal to R2 by R1 plus R2 into V. So if we convert this into a current source, the voltage across it will be still the same as our previously obtained value. If you go or zoom out, whatever value we got here is the same value. So we got the same value. So this says that if we are trying to replace any element or mainly resistive element in this circuit by an equivalent voltage or current source, it will still remain the same circuit. So neither of the KCL nor KVL will be violated. So you are free to change any such resistor. So here I have considered very simple circuit. Now, say if you want to consider one complicated circuit. So I have considered one very complicated circuit or a complex circuit. Here this is R1, R2, R3, R4, R5, P1, P2. And the current through this is say I3. So I3 is known, R3 is known. Now, first I want to convert this into equivalent voltage source. So with what value I should be replacing my R3 with? Voltage source. What will be the value of the voltage source? It will be the equivalent voltage across that element. So here the voltage across this is I into R2, which is R2 by R1 plus R2 into VN. So now here say current is known. It's a known value I3 and resistor R3 is also given. So with what value I should be replacing it with?
Sir, I3
I3R3. Yes, yes, you are right. And which terminal will be positive, left or right?
Left side is positive.
Yes, left side is positive because we should see the current is flowing from left to right. So left side is at a higher potential than the right side terminal. So we should be very careful with the potential sign, which one is positive, which one is negative. So if I replace everything in the circuit as it is, E2, R5, now I am trying to replace this with a voltage source. So the voltage source value is R3, I3, which I can replace it by a current source. So what will be the value of the current source and what is the direction of the current source? Anyone? I'm replacing it with a current source. So what will be the value of the current source? Anyone?
I3.
Yes, yes. So as current I3 is flowing through that resistor, we should replace it with a current source. And direction?
Left to right.
Left to right. Yes, because I3 is flowing from left to right in the initial circuit. So we are replacing this with the equivalent source. So we are basically replacing it with the voltage or current source, or substituting the corresponding voltage current values. So that's why it is called substitution theorem. So now we'll go to Thevenin's theorem. So anyone, Thevenin's theorem? Hello. So now we are in which theorem? Third theorem, Thevenin. So what is Thevenin's theorem? Okay, so this theorem is somewhat interesting, and it will be helpful in many applications. The proof I might or might not get time, so we'll see. First, we'll solve a few problems, and hopefully, if I get time, then I'll be able to discuss the proof. Else, it would be difficult to cover in this session. So, Thevenin's theorem says, whatever Thevenin theorem says is, say in a given circuit there are multiple number of sources, then it can be replaced by a Thevenin voltage source in series with Thevenin resistance in series with the load. So first I'll write the definition. So any circuit with multiple voltage or current sources can be replaced with an equivalent, or can be replaced with a single voltage source. Single voltage source in series with single resistance or impedance, better, single impedance and load. So what I mean to say is, first let me explain it using a circuit. Say we have a circuit something like this, a network of linear elements. So this is just a network of linear elements, and we have n number of sources, and here I am considering two sources just for the ease. And there is a load also. So this is my load impedance Z load, and my voltage source are V1, current source is I1. So now in any circuit with multiple voltage source, here I have considered one voltage or current source, but it can be multiple voltage or current source. They can be replaced with a single voltage source in series with single impedance and the load. So now this circuit can be drawn something like this. Where this is something called V Thevenin voltage. This is something called Z Thevenin, and this is called, or this is Z load. So the entire circuit, so this entire part is now replaced by this. So that is what this theorem says. So this theorem says this entire circuit, any linear circuit, these are all linear. So any linear circuit with multiple voltage or current sources, they can be replaced with a single voltage source in series with single impedance and load. So if there is such kind of circuit, then it can be replaced like this, so that we'll have a structure of one voltage source in series with two impedance. One is the single impedance, which is also called as Thevenin impedance, and this is the actual load that is there in the circuit. So now the question is, what are VTH and what are ZTH, and how to find VTH and how to find ZTH. So VTH is called Thevenin voltage. And how do we find Thevenin voltage? We'll consider the same circuit. So it would be easy if I just copy paste this. So in the given circuit, what we have to do, we have to disconnect the load. So we'll disconnect this load. So we'll disconnect this load, and whatever voltage that is appearing across these terminals, that is VTH. So you remove the load and find the voltage across the load. That will give us VTH, which is called Thevenin voltage. And ZTH, what is ZTH? Is the Thevenin impedance. So Thevenin impedance, how do we find? Thevenin impedance is also, I'll just copy paste this circuit. So what do we do in Thevenin impedance? So in Thevenin impedance, again we'll first disconnect this and keep it open. And now we'll short the voltage sources and open the current sources. So we are shorting the voltage source and opening the current source. Now we'll see from this side. So from these two terminals, we'll be looking at. So say this is our I. So we'll be looking this circuit from these two terminals and find the impedance. So that impedance is ZTH. So the Thevenin theorem, basically what it says is any circuit with multiple voltage or current sources can be replaced with a single voltage source, also called as Thevenin voltage, in series with a single impedance called Thevenin impedance, in series with the load. The Thevenin voltage is obtained by removing the load and keeping all the sources as it is and finding the voltage across those two open points, which will give us Thevenin voltage. Whereas the Thevenin impedance is obtained across the same two terminals by removing the load, and after that you need to short the voltage sources and open circuit the current sources. So in the circuit there is no impedance, no source. All the voltage sources are shorted, all the current sources are open. And when you look from this side, these two terminals, whatever impedance you see, that is called ZTH. So is this clear until this point? The terminology and how this theorem works. We'll solve with few problems, then you will be able to understand how to get this. But basic nomenclature, what is Thevenin voltage, what is impedance, and proof, I'm not sure whether I can cover it today or not. But yeah, if probably we'll get it, then we'll definitely look into it. So if you have any queries, you may ask. Okay, else we'll go to Norton's theorem. Norton's theorem is just equivalent of this Thevenin's theorem. Thevenin's theorem deals with Thevenin voltage and series. Norton's theorem deal with current source and parallel connection. So there is less than a minute. If you this meeting ends, kindly join back so we can continue our Norton's theorem. So this is our fourth theorem, also called Norton's theorem. If this meeting ends, kindly join back. We'll continue our discussion. So Norton's theorem is just same as Thevenin's theorem. We'll, instead of current voltage source, we have current source. Instead of series, we'll have parallel. So maybe it would be good if I copy paste so that you can correlate with this. You are following. Okay, I have just copy pasted this from the Thevenin's theorem. The only difference is here, if I mark it with red color. So instead of voltage source, we'll have current source. And instead of in series, we'll have parallel. So the voltage source, we are calling it Thevenin voltage. Similarly, the current source, we'll be calling it the Norton's current. And this impedance, you are calling it Thevenin impedance. This one you call it Norton impedance, or we'll see what is Thevenin impedance, what is Norton's impedance. And then you will understand. So what I'm trying to say is this itself, if I consider the same circuit, because it is for any circuit, it is applicable. So I'm considering the same circuit, so there is no issue in that. Now, whatever we are trying to say, that this circuit can be replaced by a current source in parallel with the impedance and load. So previously, it was a voltage source in series with impedance and load. Now we'll be having one current source, and the name of the current source is Norton current. So we call it Norton current, which is also represented as IN in series with Norton impedance or Thevenin impedance. Both will be same, and not in series, sorry, in parallel with the Norton or Thevenin impedance, and then with the load. So this can be drawn as what we'll be having. We'll be having one current source, right? So it should be in the other way. Current source and Norton or Thevenin impedance. And then the load. So just an equivalent of that. So this is called Norton's current, and this one is Thevenin impedance only, we'll say. And this is the load. So our circuit can be represented something like this. So any such circuit is represented by an equivalent Norton current source in series with this type of load. So we'll see how to get that Norton's current or the Thevenin impedance. So I'll just copy paste it from here so that it will save our time. Also, you can correlate directly. So in the case of VTH, it is Thevenin's voltage and Thevenin impedance. Here also, Norton impedance and Thevenin impedance are both same. So maybe they'll write Zn or ZTH. Both will be the same because the way we are finding them, it is same. And here we have. So I'll write in this way so that you can correlate easily. So here we have IN, which is also called as Norton's, not voltage, current. Okay. So in the case of Thevenin, it is voltage. In the case of Norton, it is current. And both impedances are same. So this is either ZTH or Zn, whatever way you're interested to write. And this Thevenin voltage, because it is a voltage, it is open. Now for current, it is shorted. So what we'll do is, for a given circuit, we'll remove the load, we'll short both the terminals, and we'll find the current by keeping all the voltage and current sources, and say that current is IN, also Norton current. For the impedance, Thevenin or Norton impedance, we'll remove all the, or open circuit all the current sources, short circuit all the voltage sources, and we'll look from these load terminals, and we'll see what is the impedance that we are getting, and that impedance will give the Norton or Thevenin impedance. So after getting both Norton as well as Thevenin, Norton current and Norton impedance, the overall circuit can be represented something like this, where we have current source, all are in parallel with Thevenin impedance and load. So is this point clear? I'll just summarize these two. So in Thevenin's theorem, the circuit is replaced with a single voltage source, Thevenin voltage, in series with Thevenin impedance, in series with the load. Thevenin voltage is obtained by removing the load and keeping all the sources as it is and finding the voltage across these two open terminals. Thevenin impedance is obtained when you remove the load and find the impedance across those two terminals by opening all the current sources and shorting all the voltage sources. And this is the equivalent circuit. Norton theorem says that the same circuit can be replaced by a single current source in parallel with single impedance and the load. Whereas this current source is called as Norton current, which is obtained by removing the load and shorting it and keeping all the sources as it is and finding the current in that short path, which is denoted by Norton IL. And Norton impedance is same as Thevenin impedance, and it is also the same, and it is obtained in similar way by removing the current sources and shorting the voltage sources and observing the impedance from the load terminals. So is this clear until this point? We have discussed superposition theorem, substitution theorem, Norton's theorem, as well as Thevenin's theorem. Now we'll go to compensation theorem. Is this clear until this point? If you have any doubts, please ask. Hello. Okay, we have someone mentioning in the chat. Clear, sir. Okay. Then we'll move on to our fifth theorem, which is the compensation theorem. So compensation theorem, what it says is, say we consider the same circuit. Instead of Z load, I'll consider Z plus delta Z load. Now, instead of the current I, some I plus delta I current is flowing because I have changed the impedance slightly. Of course, the current will not be the same, so it will change, and I'm considering the changes delta I. So now, how do I find delta I without actually solving the entire circuit? So this can be done by compensation theorem. So compensation theorem says that the delta I change in the current when there is a delta Z change in the load impedance can be found by considering some voltage sources and impedances here and by removing all the voltage and current sources. So just let me briefly write these things and then I'll let you know how to do this. So what it says is in any linear circuit, with multiple voltage and current sources, the delta I change, the delta I change in the load current, then delta I change in the load current for delta Z change in the load impedance. So we are changing delta Z or we are changing the load impedance by delta Z, and now I has become delta I. So for the delta Z change in load impedance, so this change can be obtained by considering a voltage source of I delta Z in series with the impedance Z plus delta Z and disconnecting and ignoring or ignoring all the sources in the circuit. So this may be somewhat difficult to understand at this point. Let me quickly draw the circuit. So we'll be using the same circuit. So let me copy this circuit. Control C, Control V. So what is the main objective is, say, uh, sorry, not this one. We have to get the original circuit. This one. So what is happening is we have this circuit. Okay. In this circuit, now Z load is not Z load. Z load, or say this Z, it is previously Z. Okay. Now there is a change in that. Now it is Z plus delta Z. Previously the current through this is I. Now, of course, the current will not be same, right? The current will change, and it is assumed that the new current is I plus delta I. Now, the objective is how to find delta I. So, using this theorem, so one way is solve the circuit and find I plus delta I. Then previously you have solved for I, you subtract them, you will get delta I. That is the very easiest, not easiest, that is the very straightforward way. Without even thinking anything, we can do. But is there any other way so that we don't have to solve the entire actual circuit again? So there you can use the compensation theorem. Forget about the proof currently. We'll just see the working. So what it says is this circuit can be replaced, or the load can be replaced by a voltage source of I delta Z in series with this impedance, and remove all the sources, whatever sources are there in the circuit. Let me just connect this. Okay. Now, first thing, we'll remove the voltage source, we'll remove the current source, and we'll also remove this. So we'll go one by one. So first, what they're saying is, just show. So what they're saying is we have a voltage source in series with the impedance. So here is the voltage source and here is the impedance. Okay. Okay. Then you short the voltage source and open the current source, because we are ignoring the sources. So it means voltage sources are shorted, current sources are open. Now the question is, what is the value of the voltage source? I delta Z. I is already calculated before and delta Z is given. And the impedance is Z plus delta Z, the new impedance. Now, if you find the current through this will be giving you delta I. So you can directly solve for delta I instead of solving for I plus delta I in the actual circuit and then subtracting. Also here there are no sources. There is only one source, one impedance, and the entire circuit you can solve for delta I. So compensation theorem is a bit tricky, and it's also a bit like complicated in the way that it is told, but it is very straightforward. We'll solve a problem on this. So compensation theorem says in any given linear circuit with multiple voltage and current sources, the delta I change in this load current for delta Z change in the load impedance can be obtained by considering a voltage source of I delta Z magnitude in series with the impedance Z plus delta Z and ignoring all the sources. So the sources means voltage as well as current. So voltage sources we are shorting and current sources we are opening. Now this new circuit, in this new circuit, the impedance Z plus delta Z will carry a current of delta I, and you can solve for delta I. So now instead of solving this actual circuit with all the sources, we can directly do this, and we can directly get delta I. So did you understand at least what I'm trying to say here, how what this theorem is all about?
Yes, sir.
Oh. Now we'll move to, so we have completed 5 theorems. There are 2 more theorems are there. One is Tellegen's theorem, one is reciprocity theorem. So Tellegen's theorem, 6th, yeah. We are in the 6th theorem. 6th theorem. Tellegen. So Tellegen's theorem says, say if you have considered two circuits having the same graph, we'll come to the part what I mean by graph. So if you consider two circuits having the same graph, then summation of product of currents in the circuit 1 with the voltages in the circuit 2 will be 0. Okay. That is the definition. We'll come back slowly. So this circuit, this is in any two linear circuits having same graph or topology. This point is clear. Having same graph or topology. This Tellegen's theorem says summation of k equals to 1 to n. Say there are n number of elements in this case as well as that case. K equals to 1 to n. Vk dash into Ik is equals to sigma k equals to 1 to n Vk into Ik dash. So okay, let me just explain what are Vk dash, what are Ik dash. So we have considered two circuits, right? Say one circuit is circuit A. Circuit A. Circuit A, each there are n number of branches, right? So for a kth branch, the voltage is Vk and current through that branch is Ik. Now we are considering circuit B. Circuit B, voltage is Vk dash and current is Ik dash. So the summation of product of these two and the summation of product of these two, Vk dash Ik and Ik dash Vk, this summation is equals to 0. So this is what this theorem says. Okay, so we'll first consider one circuit and then first I'll explain what is a graph. Then we'll get into the theory. So for this, I'm considering circuit from here so that I need not have to draw the circuit again. Okay. So this is one circuit. Okay. And this is the other circuit. So we have considered two circuits or two networks. So this is network A, this is network B. Okay. Now, what is meant by a graph or what is node and what is a branch? A branch, we have already discussed branch. So uh, any element or if you consider any node, the connections that belong to that node, they are branches. So if I say this is one branch, this is another branch, this is another branch. So the graph of any circuit, how to draw that graph. So we'll replace all the elements by a single line. So here 4 ohms is replaced by a single line. And this node will remain like a node. And now whatever element that we replace, it will show the current direction as well as the voltage polarity. So to be more clear, I'll take example of this. So any actual element will be replaced something like this. Are you following? So if we have any element resistor or any other element with current IN and voltage VN, it will be replaced by a single line. So these are called branches and they are interconnected by nodes. So if I have to write like this, so replace the elements in each branch by a single line. Okay, and then mention the current and current direction and voltage polarity. Mention current direction as well as voltage polarity. So now let us consider this thing. So this node is A. So this is A, this is B, this is C, this is O. So in between A, B, they have, let me use color. So this is this one, this is this one. And from A to C, they have this one, they have this one. So they have just denoted by random V1, I1, V2, I2. Now, A, B to C, they have considered current like this, and C to this one, they have considered current like this and current like this. So these are the branches. Okay. Similarly, if you consider these two circuits, they are different. But if you draw the graph, considering the same voltage and current polarities or the same direction, their graphs are exactly similar, isn't it? If you see, this one is A dash, this one is B dash, this one is C dash, and this one is O dash. And this current is this current, and this current is this current. And here this current is this current, here this current are these two currents. So there are two different networks, completely different, nothing in common. I mean, maybe 4 ohm resistor are in common, but their entire network is completely different. But if you draw the graph of that, both are having the identical graphs. Of course, the voltage and currents are different, but we have considered the same current polarity and voltage polarity. If you see, for any branch, the voltage is V1 and current is I1. So circuit A has V1, I1, V2, I2, V3, I3, V4, I4. And circuit B has V1 dash, I1 dash, V2 dash, I2 dash, V3 dash, I4 dash. Now in such scenarios, Tellegen's theorem says sigma Vk Ik dash equal to sigma Vk dash Ik is equals to 0. So the voltage in the node 1 multiplied by the current in the the voltage of a branch 1 in circuit A multiplied by the current through branch same branch in circuit B, and the summation of all such terms will be equal to 0. So we'll not go into the proof, but whatever Tellegen's theorem says, sigma Vk dash multiplied by Ik is equals to sigma Vk times Ik dash is equals to 0. So this is what Tellegen theorem says. So is this point clear? Like this will be applicable only for circuits having the same graph or topology. So if they have a different graph, then it is not applicable. So circuits having same graph or same topology, if you calculate voltage and currents in all the branches of circuit A as well as circuit B, then summation of product of voltages across the branches in circuit A and currents in the branches in circuit B. Similarly, the vice versa, this summation will be equal to 0. Is this clear? Tellegen's theorem. Hello, are you following? Someone has mentioned in the chat. Yes, sir.
Yes.
Okay. Okay. So this is Tellegen's theorem. Now we'll get back to reciprocity theorem. So reciprocity theorem is our 7th theorem. So there are a lot of theorems in this week, and it may be a bit heavy for you, but you try to understand and solve few problems. Also, we'll be solving 2 to 3 problems today, and try to understand the theorems because these are very important theorems. And you need to remember these theorems, and it will actually save our time while solving some complicated problems. So reciprocity theorem basically says we'll consider a two-port network. Two-port network means inside input side there is one port, output side there is another port. So in this two-port network is said to be reciprocal if the ratio of response to excitation is same even if you interchange the uh, response and excitation. Okay, just let me write. So a linear circuit. So here it is only purely resistive. So a linear circuit or network is reciprocal if the ratio of response to excitation remains same even if we interchange the response and excitation. So yeah, it may be somewhat confusing, but let us quickly consider a circuit. When I say here reciprocal, this is only applicable for passive network. So keep that in mind. Passive network means only resistor. There are not any active terms or active elements. Passive network. So we'll consider one network. So basically, it's a two-port network. So this is that linear network. Okay. Now it's a two-port network, right? So input side we have two outputs, output side we have two outputs. Now what we'll be doing is when we say response to the excitation, so we are exciting it with some voltage and we are getting the current on the other side. So say input side we are exciting with voltage plus minus, and output side we are shorting. Say the voltage is V1 and the current is I1. So the response, the ratio of response to the excitation. So uh, in this case, this is our excitation and this is our response. So the ratio is this I1 by V1. Now this ratio should remain same even if you interchange the excitation and response. So now what I will be doing, I will be considering the same thing. I'll consider the same network, but I'll change my excitation and response. So now we have this two-port network. Two-port network. Now I'll excite it with the voltage here, plus minus, and here I'll short it. Say the voltage is V2 here, and now the current is I2 here. So now this becomes the excitation, and this becomes the response. Okay. So now the ratio is I2 by V2. So this reciprocity theorem says if this ratio is same, then that network is reciprocal. Assume that this network is reciprocal, then these ratios will be same. So we are having I1 by V1 is equals to I2 by V2. So we have excited it at two different ports. So again, this is a two-port network because it has two ports. This is port 1 and this is port 2. So two ports are accessible to us. We can either connect a voltage source on the port 1 or voltage source on the port 2. So basically we are exciting it with a voltage source in the port 1 and getting the current in the port 2, and in the other case exciting it with voltage in the port 2 and getting the current in port 1. So reciprocity theorem is quite simple and straightforward. So in a linear circuit, if it is reciprocal, the ratio remains same. The ratio of response to the excitation remains same even if you interchange their location. So that is the end of the theorems. But before I summarize, I just want to also highlight the star delta transformation. So this is one result which is quite famous, and you might have also studied in your +1, +2 or UG. So star delta transformation is very important so that at cases we can convert star into delta and delta into star. And it will simplify the circuit very much and it will save a lot of time. So there might be cases where you need to convert star into delta so that the circuit becomes much simpler and you can uh, like do it very easily. And these results you need to remember, but it does not mean that you have to remember throughout your life. Of course, we keep on forgetting, but whenever it is needed, you should go through and remember. So as long as this course is concerned, you need to remember this, and as long as you're studying, you need to remember. But yeah, I don't remember. But every time you need something, you have to go revise your concepts. But I'll be giving this formula. So here I have the formula. First, so is this star connected or delta connected? Anyone?
Delta connected.
Delta connected, yes. So RA, RB, RC, and the terminals are X, Y, Z. So in the same X, Y, Z, now we are representing it with star. Okay, now say the resistances are R1, R2, and R3. The terminals are same X, Y, Z. So now there is a relation of RA, RB, RC in terms of R1, R2, R3. Similarly, R1, R2, R3 in terms of RA, RB, RC. So I'll just quickly write them down. So RA is equals to R1, R2 plus R2, R3 plus R3, R1 by R1. Because R1 is coming opposite of RA. So however you want to remember, you can remember, but I'll just write down the values. And RB is, here the numerator remains same, only the denominator will change. R2, R3 plus R3, R1 by R2. And RC is R1, R2 plus R2, R3 plus R3, R1 by R3. So this is when star is given and you want to convert it to delta. What are the values of the resistor or impedance in that delta? Similarly, if delta is given and you want to convert back into here, so what are the values? Now, R1 is equals to R2, R3 or RB, RC by RA plus RB plus RC. RB, RC by, here the denominator remains same and numerator keep on changing. Similarly, R2 is equals to RA, RC by RA plus RB plus RC. And similarly, R3 is equals to RA RB by RA plus RB plus RC. So this is just a conversion formula which you can remember, or you have to remember, I would say, so that at times it will save a lot of time and you can solve the any problem much easier. And also it will save time. So before we go into the problem solving session, I'll just summarize whatever network theorems we have discussed today. So yeah, previous weeks we have discussed about analysis, mainly mesh and nodal. In today's network theorem discussion, we have first started with superposition theorem, followed by substitution theorem, then Thevenin's theorem, Norton's theorem, as well as compensation theorem, and we have discussed Tellegen's theorem, reciprocity theorem, followed by star delta transformation. In superposition theorem, it is very simple. If any linear circuit could have multiple voltage or current sources, then the response of any element, maybe voltage or current, is the algebraic sum of responses obtained by considering one source at a time. So current source will be open, voltage source will be short circuited, and we'll consider each source at a time, and then we'll calculate the response and do algebraic sum. Substitution theorem says if any or in any linear circuit with multiple sources, any resistor element can be replaced by its equivalent voltage source or current source. So first we'll calculate the voltage across the that element, and either we replace it with that voltage source, equivalent voltage source, or the current. And it is also straightforward. Thevenin's theorem and Norton's theorem are just analogous to each other. So in Thevenin's theorem, the given circuit with multiple voltage or current sources can be replaced with single voltage source in series with impedance and load. Here it is single current source in parallel with the impedance and load. The Thevenin, so in this case, the voltage source, which is the Thevenin voltage, is obtained by opening the load terminal and finding the voltage across that. Impedance is found out by shorting all the voltage sources, opening all the current sources, and finding the impedance at the two output ports. Norton's current is obtained by shorting this load and keeping everything same and finding the current through that path. And this impedance is also the same thing. Compensation theorem is a bit tricky. So in this given circuit, the change in the delta I current for delta Z change in the impedance can be found out by replacing the circuit with a voltage source of I delta Z in series with impedance Z plus delta Z, and ignoring all the voltage and current source. So short the voltage source, open the current source. Now the current through this is delta I. Directly you can solve for this to get delta I. Tellegen's theorem says two linear circuits having same graph or topology, the product of voltages of circuit A with currents of circuit B, or summation of product of voltages with circuit A and current of circuit B, or the vice versa, there it is zero. So it lies on the fact that both circuits or networks should have same graph, else it will not work. And reciprocity theorem says it's a linear circuit. If a linear circuit is reciprocal, then the ratio of response to excitation will remain same, even if we interchange the response and the excitation. And it's based on two-port network because we are changing the excitation and response, and the ratio will remain same. Then we discussed about star delta transformation, which will be crucial if there are any star or delta shape in the circuit. There is less than a minute, so if you have any queries, you may ask, else we'll go to problem solving session. So till now we have discussed around 7 network theorems and star data transformation, and now we'll be using them to solve few problems last year assignment problems. Do you have any queries till now? Hello. Hello.
Yes, sir.
Okay. Okay, then we'll let this meeting end, then we can start. So now we'll move on to our problem solving session. So whatever theorems we have learned today, we'll be using them for solving these problems. Okay, so where are we? We'll open our previous assignment and we'll solve few problems. Okay, so the first problem is, yeah, so this is our first problem. Let me just copy. So it is based on Thevenin's theorem. Okay, so yeah. So this is our problem one. So just read the problem. Wait a minute. No, just okay. Just go through the problem. Just have a look at it. Okay, have you gone through the question? Okay, have you gone through this question? Okay, so first part, they are saying they have open circuited this and they have given the voltage. Second part, they are saying they have short circuited this and they have given the current. So if we correlate with the knowledge we have gained today, so if we are open circuiting and finding the voltage, it's a Thevenin voltage. If you are short circuiting and getting the current, it's a Norton current. So basically, whatever they have given, it is Thevenin voltage and Norton current. So this is Thevenin voltage. This is Thevenin voltage, and this is Norton current. And RAB is the load. So this is the load we will connect at the end, and they are giving the load current. So using Thevenin's theorem or Norton's theorem, you have to calculate what is the current through this load. So first, if you carefully see, using Thevenin's theorem in Laplace domain, so they have given it time domain. So these are like level by level things. Previously, we have started with analysis everything. Then last week we have learned Laplace transform. Now we are learning theorems. So these theorems are applicable to circuit, whether you do it in time domain or do it in S domain, it is still applicable. But as S domain is much more simpler for us because there will not be any exponential term. It will be just like fraction of S terms. So we'll proceed with the Laplace domain. So first we'll be writing Thevenin voltage. So here we have VTH is 10 into 1 minus e to the power minus t by 2 into u of t. Now apply Laplace transform. Now can you tell me what will be the Thevenin voltage in Laplace transform after applying Laplace transform? Anyone? Hello. VTH of S. I want VTH of S. Yeah.
10 into 1 by s minus 1 divided by s plus t by 2.
Yes. S plus 1 by 2 because t will be removed, only the constant. Now, if I simplify this, you also simplify, we will get something like this. 5 by S into S plus half. Okay. So this is my Thevenin voltage in S domain. Okay. Now, Norton current is 4u of t. So Norton current IN of t is 4u of t, right? 4u of t. Now, if you apply Laplace transform, what you will be getting?
So 4 by s.
4 by s, yeah, you are right. So we'll get 4 by s, it is straightforward. In of s, sorry. In of s is 4 by s. So we have Thevenin's voltage and Norton's current. So for us to solve this circuit, what else is needed? Either the Thevenin impedance, so that we can get a equivalent series network, and then we can solve. But here they have not given Thevenin impedance. So how do you think we can proceed? Or have they given information to find the Thevenin impedance?
Sir, we know the Thevenin's voltage and Norton's current.
Yes.
Can we find it by V by I?
Yes, yes. So Thevenin voltage by Norton current is Z Thevenin. So this is one important thing. I'll also prove how it is coming. So Z Thevenin is V Thevenin by I Norton. Very good. So this is the information that they have provided, so that we can calculate ZTH. So how this is coming? So any given circuit can be represented by a voltage source and V Thevenin and Z Thevenin and Z, or current source and Z Thevenin or Z Norton and Z, right? Okay. So this is I Norton, this is Z Thevenin, and this is Z. Okay, fine. Now, irrespective of whatever you do or whatever approach you do, the current through Z remains same, isn't it? So the current through this remains same, because the voltage across Z should remain same, because both are giving the same information. So the current through Z or the voltage across Z in either of the cases should remain same, because they are just the same circuit in a different representation. So now if you do that, what is my I? My I is V Thevenin by Z plus Z Thevenin in the case, this case, or I Norton into, sorry, I Norton into Z Thevenin by Z plus Z Thevenin as coming from this circuit. So now if I cancel this and this, I'll be left with one expression, which is VTH is equals to I Norton into ZTH. So this is the relation between these two, which also someone has pointed out. Yeah. From there, we'll be getting the ZTH. So let me take a new page. And so whatever we have here, VTH and I Norton, let us just copy paste and take it to next page. So we have here VThevenin and we have here I Norton. So from this, we'll find Z Thevenin. So how are we finding Z Thevenin? V Thevenin by I Norton, right? So I'll directly get Z Thevenin. So Z Thevenin is V Thevenin by I Norton. So if you do 5 by 4, 1.25 by S plus half. Is my calculation correct? You correct me if I'm making any mistake.
Yes, sir. Correct.
Yes. So now, thank you. Now we'll get back to our knowledge or our concept that this circuit can be replaced by VTH, ZTH, and load in series, everything in series. So now we'll do the exactly same thing. Whereas here the load is 2 ohm. Okay. So I'll connect a circuit. Okay. So this is my V Thevenin of S, and this is my Z Thevenin, and this is my Z load. Okay. So 2 ohm is given. So if I do Laplace transform, what I will be getting?
2 itself.
2. Sorry. Hello.
2, sir, 2.
2. Yes. This is the tricky part. 2 will not be becoming 2 by S. That is a voltage source or any other constant or current source. But resistor, we have seen that R will still remain as R in the case of uh, Laplace transform. So R will still remain R. Now, whatever they're asking, we'll see what is the current flowing through RAB. So we are asked to find what is the current flowing through this. Say I will call it I load. Now I know I load is equals to V Thevenin of S into 1 by Z Thevenin plus Z load. You agree, right?
Yes, sir.
So we'll substitute all the information. V Thevenin of S is 5 by S into S plus half, and 1 by Z Thevenin of S is 1.25 by S plus half, plus Z load is 2. So we'll simplify this. We'll be getting something like this. So my I load of S. So as it is in S domain, it is important we use capital letters. That's just a notation. So let us follow that only. I load of S is equals to, we'll have 5 by S into S plus half into S plus half by 2S plus 1 plus 1.25. So 2S plus 2.25. Now this will get cancelled with this, and we will be left with 2.5. I will take common 2 in the denominator by S plus 1.125. Is this okay?
Yes, sir.
Okay. So now partial fractions you can do, but the simplest way is multiply by 1.125 divide by 1.125. This is simpler. Why? Because now I'll get I load of S is equals to 2.5 by 1.125 into 1.125 by S into S plus 1.125. Okay. Now this part can be written as 1 by S. Okay, green is not making it. 1 by S minus 1 by S plus 1.125. So inside the bracket, whatever is there, we can simply write in this way. So for that, we need 1.125 in the numerator. For the same reason, I have considered 1.125 in the numerator and denominator, and I have accordingly changed. So now my I load of S will become something like this. My I load of S. So it is 2.5 by 1.125. I have calculated it is coming around 2.22 into 1 by S minus 1 by S plus 1.125. Now what is I load of T? So inverse Laplace transform we are doing. So can anyone tell me what is this? Convert this into T domain. So 1 by S is 1, 1 by S plus A is e to the power minus 18. So can anyone say?
1.22 multiplied 1 minus e to the power minus 1.25t.
Yes, 1.125. So this is 2.22 into 1 minus e to the power minus 1.125t, everything into u of t. So this is the expression that I got for I load of t. Now I'll go back to the question and I'll see what they are asking and whether my answer it is matching with them or not. So this is my 2.22 1 minus e to the power minus 1.125. So let us go back here. So what is the value of a here? So
2.22
yes, 2.22. So it is matching. And what is the value of b?
minus 2.22.
Minus 2.22. So minus 2.22, it is matching. And it is e to the power t minus tau, but we have e to the power minus k tau. So what is tau? Maybe this 2 is
1
not.
divided by 1.1.
Yes. Can you tell me what is the value? Quickly. So it is
0.88 seconds.
0.88 seconds. Okay, let us check. 0.88 seconds. So it is in this given range only. So that's how we use Thevenin's theorem. So if we see, like, they have not given any information about this RC, whatever, but they have given some information that VAB is Thevenin voltage when the load is removed, and the current through this when this is shorted is Norton current. So they have given Thevenin voltage in time domain, Norton current in time domain, and they have given load and they are asking RAB. Now, Thevenin voltage, first basic thing is we have converted everything into Laplace domain, Thevenin voltage as well as Norton current. Now, one information it is missing is the Thevenin impedance, which we found out from the Thevenin voltage as well as Norton current because they're related, and which we have also proved. So now I got Thevenin impedance. Now there are two ways, either use Thevenin's theorem or Norton's theorem. It is up to your personal choice, but I am more comfortable with Thevenin's theorem because it is in series connected and this is parallel. So I usually do this one, but you can still go with Norton's theorem and you will still be getting the same result. It is up to your personal choice which theorem you are more comfortable with. I am more comfortable with Thevenin's theorem, so I have considered Thevenin theorem. And Z load is 2. It is not 2 bias. Kindly note that impedance, the resistance will remain same in S domain. So Z load is 2. V Thevenin is known. Z Thevenin is known. I have substituted and then I got one expression for I load of S. Then I have applied partial fractions, not derived, but cleverly I have converted this into small fractions and then we have applied inverse Laplace transform to get I load of T. So based on the whatever they were asking, so A is 2.22, B is minus 2.22, and how much tau you get? 0.88. How much are you getting? 0.88.
Yes, sir.
Okay. So this is the values we got. Okay, so this is how we use Thevenin's theorem, or you can use Norton's theorem to solve this question. Now, let me see, there is this important thing, which is this question. So here, can you tell me which theorem we need to use to solve this question? Just have a look at it.
Compensation theorem.
Compensation theorem, yeah, you are right. So we'll be using compensation theorem. So I'll first correlate with our the theory we have learned, and then we can get it. So yeah, this is the question. Let me create a new page. So we are in problem 2, and problem 2 is compensation theorem. This seems a little bit tricky, compensation theorem, but when you solve one problem, then you will feel more comfortable and confident. So this is our problem 2. Okay, and this is compensation theorem. This is a very simple and straightforward, but it might look like complicated. So they have given this circuit, and initially R is 2 ohm. Now they have changed R to 15.45 ohm. And previously current I3 is say I3. Now they are asking what will be the new values of I1, I2 and I3. So this is what they are asking. So just tell me here what is the value of R?
2 ohms.
2 ohm. And delta R?
15.45 minus 2.
Yes.
13.45.
Yes, good. 13.45 ohm. So I know R, I know delta AR. And I'll go back to my theorem. So I'll just directly correlate with that. Where is the theorem? So the theorem is here. So let us just take a screenshot of this thing. And we'll go here and we'll use the same thing. So if my circuit is given something like this, so then I have to, sorry. So then I have to create this circuit. Okay, so kindly take a very good note of the direction of the currents and the polarity. So it should be in the same polarity. So the current is coming like this. So what is the value of I here? The I that was previously entering Z, what was that I value? So when there is no change,
13 amperes.
how much?
13 amperes.
13 ampere. Because this is 4 amperes and this is 9 amperes. So by applying KCL, you will get this one 13 ampere. So now I do not know about anything about this circuit. How will I proceed? But I know this compensation theorem. So I know delta Z, I know Z plus delta Z, and I know what to do with the circuit. So what I'll do, I will short these two. I'll replace this R plus delta R, whatever, with this kind of circuit. So here 7 ohm, 13 ohm. So I'll redraw the circuit. Okay. Seven ohm, 13 ohm, and this one a voltage source and a resistance. Okay. Now, what are the resistors? 7 ohm, 13 ohm. 7 ohm, 13 ohm. And this is how much? What is the value of this voltage source? I delta Z.
I delta Z.
So, what will be the value of that one? Can someone calculate?
174.85.
Sorry, 170?
174.85.
Yes,
Volts.
174.85 volts. Thank you. And what will be the value of this impedance?
15.45.
15.45. Okay. Yes. So we have recalculated or redrawn our circuit so that our main intention is to find the currents. So now we have seen from this circuit, now the currents are just incremental changes. So what we are trying to say is this is delta I3, this is delta I2. Careful with the direction now. Delta I1. So now this circuit will have only the incremental changes, delta I1, delta I2 to delta I3. But my circuit, my theory says the current should go from top to bottom. But my circuit says it is the other way around. So what happens? My delta I3, delta I2, delta I1 are negative. But I keep that in mind while solving. So how to solve this? So first we'll convert this 17 and 13 ohm into a single resistor. Okay. So what will be the parallel of 7 and 13 ohm? Can someone calculate and tell me?
4.55 ohms.
4.55. Okay. Four point 55, right? Okay. and this is 15.45 ohms. Sorry, this is not volt, this is ohms. And this is 174.85 volt. So now the current direction will be in this direction, right? So which is minus delta I3. So can you calculate and tell me what is delta I3? V by summation of Z.
8.7425.
8.74.
Minus 8.7.
Yes, yes. Minus 8.7425. Minus 7425. Okay. So my I3 is obtained. And what is the relation between delta I1 and delta I2?
Current divider rule.
Yes, current dividing. So I can write my delta I1 will be 13 by 13 plus 7 into delta I3, and the delta I2 is 13, so 7 by 13 plus 7 into delta I3. So can you calculate? And I think only Kavya is doing. What about others? Are you doing? Are you following? If you have any doubts, you may ask. So I will repeat it again.
I1 is minus 5.68.
Minus 5.68. Okay.
I2 is minus 3.059.
I1 is minus 5.68. Sorry, this is amperes. I have mentioned here volt. This should be ampere. And the other one is
Minus 3.059.
0.59 amperes. Oh. Now, these are the incremental changes. Now, the actual circuit will have I plus delta I, and they are asking what are the new values of I1, I2, I3. So the new values will be I plus delta I plus delta I2, I plus delta I3, right? So I1 dash is equals to I1 plus delta I1, I2 dash is equals to I2 plus delta I2, and I3 dash, these are the new values, equal to I3 plus delta I3. So can you tell me what are the values of I1, I2, I3? New I1 dash, I2 dash, I3 dash. I1 dash is minus 5.68 plus 4, minus 1.68, right? And I2 dash is minus 3.059 plus 9. So how much? 4 point something or 5 point something?
5.94.
5.94. And I3 is 13 plus minus 8.74. So 13, 5, 4.3 or 4.26 something. How much?
4.25726.
4.2. 4, how much? 4,
26.
26.
4.26.
26 numbers. So these are the new currents that we are getting. Okay. So we'll check. I1 is how much? Minus 1.68. It is in the range. I2 is 5.94. It is also in the range. And I3 dash 4.26. It is also in the range. So this we have considered two important theorems. Problems, where one is Thevenin's theorem, the other one is uh, compensation theorem. But I have just now realized that I have forgotten to discuss one more important theorem. So let us quickly do, which is also the maximum power transfer theorem. I'll just directly give the results as we are running out of time. power transfer theorem. So maximum power transfer theorem lies around the fact that if you have a variable load resistance or load impedance, what should be the load so that maximum power is transferred to the load. So the basic idea or how to proceed with this is, say one variable is low, vary, find the power expression and then differentiate it with respect to that variable term, and at maximum power the derivative is 0. So that's how we solve, but we'll not be going into all the details. So this is Vs and this is a source impedance and this is the load impedance, and say the source impedance has Rs plus jXs because it is coming with the source, and load impedance RL plus jXL. This is the source impedance and it is there. So what should be my load, or how should I vary my load so that maximum power is transferred to the load? So there are three cases I'll directly give. One is case one. Case one is XL is variable. So in that case, XL should be minus XS. So they should cancel with each other and it will be purely resistive circuit. And case 2. Only RL is variable. So XL is fixed, only RL is variables, and we have to differentiate it with RL. In the previous case, you will differentiate it with XL. So if RL is variable, then we'll have something like this. RL is equals to square root of RS square plus XL plus XS square. So you can also get this expression, you have to differentiate it, but you'll be getting this. Case 3 when both are variable. So case 3 is simple, just combining case 1 and case 2. So both RL and XL are variable. So from the first case, we will get XL is equals to minus XS. And from the second case, you will get RL. What is RL? RS square plus the other square. And if you substitute this one, that will become 0. So RL is equals to RS. So maximum power will be transferred when there is no impedance and it is purely resistive, and the resistance should be equal. So this is one important theorem which we have missed in today's discussion. Yeah, so that is it for today. To summarize, we have started with network theorem introduction. First, we discussed about superposition theorem. Then we discussed about substitution theorem. Then we discussed about Thevenin's theorem, and its analogous equivalent theorem is the Norton theorem, followed by compensation theorem, which is a bit tricky, but it's a very important and it's a good theorem, followed by Tellegen's theorem and reciprocity theorem. Then we have also seen star delta transformation. So in any circuit, you could easily solve if you directly convert into star or delta, depending upon the application. Then we have solved few problems, whereas in the problem 1, we considered Thevenin's theorem. So Thevenin voltage Norton current is given. We have calculated the impedance, the Thevenin impedance, and then we have applied Thevenin's theorem to calculate the current and applied inverse Laplace transform to get the these things. In the second case, compensation theorem, they have changed the resistance. So we have exactly drawn whatever we have learned today, and following the same conventions, we have realized that delta I1, delta I2, delta I3 are coming negative, but we have still proceeded with the negative values because it could be negative depending upon things. So for changing, so when the resistance is increased, the current is decreasing, which is also fact. So it may not always, you should not always think that R is increased, so I plus delta I is positive, but it is not like that. If I'm increasing the resistance, current will decrease. So delta I will be negative, so current is decreasing. So we should like also make sure that whatever we are doing is correct. So it is also logically correct. So that's why my current change is negative. But you should keep in mind these polarities and current directions. It may come negative, but you should not do any mistake in the polarity and current directions, followed by maximum power transfer theorem. I have just given 3 cases, which you can also solve during your free time, and you can get these expressions. Yeah, that is it for today. It is mainly about brief summary of network theorem and how and where we can use the network theorem. I could not get time to prove the network theorem, but yeah, if you have any queries in whatever we have discussed today, you may ask. And how is your assignments going on? Are you able to submit? Is this session helpful? I mean, are these sessions helpful? Or if you want anything else, then also you can inform me so that we can make changes accordingly and proceed. Yes, sir, helpful. Okay, thank you. And what about others? Are you following? Are you going through the lectures? Are these helpful?
Yes.
Yes. Okay. And how are you doing in your assignments? Are you doing good? Yes, I'm good. Okay. Yeah, if you have any queries, you can reach out to me either in the YouTube video comment section, or you can mail me, or you can post questions in the forum where Professor Abhishek Chatterjee will be replying to your doubts. Yeah, that is it for today. If you have any queries, you may ask, else we can end this session here.
Sir,
Yeah.
when we use the compensation theorem,
Mhm.
sir, voltage sources are always short circuited, or it is when it is ideal, then we have to short it.
Yes, yes. First of all, there is less
Otherwise,
than a
we have to
minute.
set-
So if this meeting had kindly join back, so we can continue our discussion. Yes. So coming to your question, these voltage sources are shorted, but these voltage sources, they have not said anything that they have impedance or any such information. So we have directly shorted, keeping the resistance. But if they have any impedance series, then you have to keep that series impedance wise.
Okay, thank you.
Okay. Yeah, if you do not have any question, this meeting will end. Yeah, then we can wind this session up. Thank you for joining. Good night. All the best for your assignments. Okay, then see you next week. Bye.